Right now, an invisible force is wrapped around our entire planet, holding back a storm you cannot see. It never switches off. You have never felt it, and you cannot touch it. But without it, the sky above you would slowly turn deadly. So what exactly is this shield, and what would really happen if it disappeared? The thing protecting us is Earth's magnetic field. Deep below your feet, almost 3,000 kilometers down, there is an ocean of molten iron, hotter than 5,000 degrees. As that liquid metal churns and spins, it works like a giant natural generator, producing a magnetic field that reaches far out into space. Scientists call this huge magnetic bubble the magnetosphere. It is shaped a little like a comet, rounded on the side facing the sun, and stretched into a long tail on the night side. It is completely invisible to your eyes, but it is one of the most important features of our entire planet, and it has existed for billions of years. The field lines emerge from near the South Pole, arc outward through space in great invisible curves, and loop back down toward the North Pole, like the lines you would see if you held a magnet under a piece of paper covered in iron filings, only stretched across the entire planet. On the day side facing the sun, the magnetosphere reaches out roughly 65,000 kilometers into space. On the night side, that tail can stretch 600,000 kilometers, almost twice the distance from Earth to the Moon. And tucked inside this invisible structure are two donut-shaped regions of trapped radiation, known as the Van Allen belts, which ring our planet like a pair of invisible life rings. Every living thing on Earth, every human being who has ever existed, has grown up, lived, and died inside the protection of this ancient, invisible shell. Here is why it matters so much. The sun is not calm and steady. It constantly blows out a stream of electrically charged particles at around 1,000,000 miles per hour. We call this the solar wind. If those particles hit our air directly, they could slowly strip it away over time. But Earth's magnetic field gets in the way first. Because the particles carry an electric charge, the magnetic field bends their paths, steering most of them around the planet, a bit like water parting around the front of a fast-moving boat. Sometimes the sun does something far more violent. It can hurl a gigantic cloud of plasma and magnetic energy out into space. Astronomers call this a coronal mass ejection. When one of these slams into Earth, it squeezes our magnetic field and sets off what we call a geomagnetic storm. Think of it like this. Imagine throwing a bowling ball into a soap bubble. The bubble does not pop, but it deforms, it shakes, and the whole thing trembles. That is roughly what happens to our magnetosphere during a strong CME strike. The pressure from the incoming cloud compresses the day side of the field, pushing it closer to Earth, while the night side is stretched and pulled into a long, whipping tail. These eruptions travel across the 150 million kilometers between the Sun and Earth in anywhere from 15 hours to 3 days, depending on how fast the cloud is moving. The largest ones can travel at over 3,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 2 minutes. When they arrive, the impact is not quiet. Charged particles pour into the upper atmosphere near the poles, electrical currents surge through the ground beneath our feet, and the sky above the polar regions lights up in one of the most spectacular displays nature can produce, the auroras. In the strongest storms, that energy can push surges of electricity through power grids and damage satellites in orbit. A famous storm in 1989 knocked out the power across the whole of Quebec, in Canada, for hours. Our magnetic field is the main thing standing between us and the full force of these solar blasts. But here is the surprising part. Our shield is not as steady as you might think, and right now, it is getting weaker. Over the last 200 years, the magnetic field has lost around 9% of its strength on a global average. And there is one spot where it is especially weak. It stretches all the way from South America to Southern Africa, and it is called the South Atlantic Anomaly. Inside it, the field has dropped so much that satellites passing overhead get hit with extra radiation, and they sometimes glitch or shut down. Satellite measurements show this weak zone has been growing, drifting slowly westward, and is even starting to split into 2 separate centers. Here is where it gets genuinely surprising. The International Space Station passes through the South Atlantic Anomaly on almost every orbit. Astronauts inside the station sometimes see unexplained flashes of light, even with their eyes closed, caused by high-energy particles passing directly through their retinas as the station crosses the anomaly. That is not science fiction. That is a real, documented experience reported by astronauts since the earliest space missions. The Hubble Space Telescope, one of the most sophisticated instruments ever built, automatically shuts down certain sensitive observations every time it passes through this weak zone because the extra radiation scrambles its detectors. Engineers have to schedule Hubble's scientific work around the anomaly the way you might plan a road trip around a storm. And the numbers behind this weakening are striking. Inside the anomaly, the field strength has dropped from around 24,000 nanoteslus in 1970 to around 22,000 nanoteslus by 2020. That is a fall of roughly 8% in just 50 years, in a single region. What is driving it? Deep beneath southern Africa, scientists have found a mysterious dense mass of rock sitting at the boundary between the outer core and the mantle, almost 3,000 kilometers down. This structure appears to be disrupting the normal flow of liquid iron, creating a patch where the magnetic field is actually reversed, pushing against the main field from below, like a current swimming upstream. It is one of the most remarkable geological puzzles on the planet, and it is happening right beneath our feet, right now. So if the field is weakening, it is fair to ask the big question. What if it didn't just get weaker? What if it disappeared completely? To answer that, we don't only have to guess or run computer models. We can look at a real planet that already lost its shield. But before we get there, consider this. We actually have a glimpse, from our own past, of what a severely weakened magnetic field looks like. Around 42,000 years ago, Earth's magnetic field did not reverse completely, but it came very close. The field temporarily collapsed to just 6% of its current strength, a period scientists call the Lechamp excursion. For roughly 1,000 years, our planet was almost magnetically naked. During that time, far more cosmic radiation, high-energy particles from deep space, poured through the atmosphere than normal. The ozone layer was partially disrupted. Auroras would have appeared not just near the poles but across the entire sky, every night, visible from the tropics. The world would have looked dramatically different just by looking up. Scientists studying ancient trees, ice cores, and cave sediments from that period have found clear chemical fingerprints of that extra radiation baked into the geological record, like a scar left in the Earth itself. It is one of the most powerful reminders that this shield we take for granted has flickered before, and the consequences were real and measurable. Now imagine not 6%. Imagine 0. Imagine the field not just weakening but switching off entirely. What would actually happen, and how fast? The answer, it turns out, is far more nuanced than most people expect. Because the field would not vanish overnight, physics tells us it would take roughly 15,000 years to fully fade away. That is longer than all of recorded human civilization. In the short term, meaning decades, the most immediate effects would be on our technology, not on our bodies. GPS satellites would be thrown into chaos. Power grids in high-latitude countries would be increasingly vulnerable to geomagnetic disruptions. Radiation exposure for pilots, frequent flyers, and astronauts would climb significantly. The sky above would change, auroras would blaze across latitudes that have never seen them. But the deeper question, the one that haunts planetary scientists, is what happens over millions of years. And to answer that, we do not have to imagine. We have a perfect natural experiment sitting just next door in our solar system. A planet that went through exactly this, and has the scars to prove it. That planet is Mars. Today, Mars is a freezing, dry desert. But billions of years ago, it was a very different world, with rivers, lakes, and a thick atmosphere. Mars once had a magnetic field too, but its core cooled down, and that field switched off, somewhere between about 3.5 and 4 billion years ago. Mars was once genuinely, deeply wet. We can even still find the ghostly fingerprints of the old magnetic field, preserved in ancient magnetized rocks in the Martian crust, particularly in the ancient highlands of the southern hemisphere. These rocks locked in the direction of the field when they cooled billions of years ago, like a fossil compass frozen in time. They are the only remaining evidence that Mars was once magnetically alive. But then something changed deep inside the planet. Mars is smaller than Earth, roughly half the diameter and only about 11% of the mass. Because it is smaller, it cooled faster. Scientists believe this happened by roughly 3.7 billion years ago, though the exact timing is still being refined as we gather more data from Mars missions. After that, Mars was exposed. After that, the solar wind had nothing to stop it. NASA's MAVEN spacecraft has shown that the Sun is still stripping gas off the top of Mars's thin atmosphere today, at roughly 100 grams every second, and that loss jumps higher during solar storms. Over billions of years, a warm, wet world slowly became the barren red planet we see now. Now, scientists are careful here, and so are we. The story is not quite as simple as, lose the field, lose the air. Venus has almost no magnetic field, yet it holds onto a thick, heavy atmosphere, and some studies find that planets with and without magnetic fields lose gas at surprisingly similar rates. So the magnetic field is not a perfect, magic force field. But what it clearly does for us is protect us from radiation. If it vanished tomorrow, our air would not blow away overnight. The real and immediate danger would be the radiation reaching the surface, the satellites failing, and the navigation and power systems we rely on every single day being thrown into chaos. Let's listen to the magnetic field music. They sound like a dawn chorus of chirping birds. Researchers were so struck by this that they literally named them chorus waves. And those same charged particles from the sun, sliding down our magnetic field near the poles, create the most stunning proof that the shield is real, the auroras. What you are seeing is not just a light show. It is a collision. As the charged particles from the sun are funneled down along the magnetic field lines toward the poles, they slam into the gas molecules in our upper atmosphere, roughly 100 to 300 kilometers above the ground. And when they collide, those gas molecules light up. They absorb the energy of the impact and release it as light, the same basic process as a neon sign, only happening across hundreds of thousands of square kilometers of sky. The colors tell you exactly what is happening and at what altitude. The most common color, that vivid, electric green, comes from oxygen molecules being struck at around 100 kilometers up. Higher in the atmosphere, above 200 kilometers, oxygen produces a deep, rare crimson red. The blue and purple fringes you sometimes see at the lower edges come from nitrogen molecules joining the collision. Each color is a chemical signature, a specific atom or molecule announcing exactly what it is and where it sits in the sky. The auroras on Earth and the auroras on the night side of the planet are always happening simultaneously, a glowing ring around the North Pole perfectly mirrored by a glowing ring around the South Pole, both lit at exactly the same moment by the same stream of particles, because the magnetic field lines connect them. North and South, lit together, like two ends of the same invisible wire. These shimmering curtains of green and red light, seen here from the International Space Station, are not just pretty. They are the visible signature of our magnetic field doing its job, catching the sun's particles and guiding them safely away from us, down toward the poles. So here is the fact to leave you with. The last time Earth's magnetic poles completely flipped, with north becoming south, was around 780,000 years ago, an event named the Brunhes-Matayama reversal. A compass back then would have pointed the opposite way. It has happened many times before in Earth's history, and one day, it will happen again. Our invisible shield is always shifting, always changing, and we are only just beginning to learn how to listen to it.